All right, everyone, welcome once again to the set theory seminar. Today we have Vladimir Kanovei so I have to look this up on from the Institute for Information Transmission Problems in Moscow. And Vladimir, I have wanted to hear you talk for such a long time, so this is a great pleasure. I was so happy that you agreed to give a talk. I think this is a great opportunity, so thank you so much. All right, go right ahead, Vladimir.
Thank you very much. So I'm very happy to give this talk. It's not my first one in New York. Previous ones were in person, and this one is by internet.
When did you speak in New York?
Sorry?
When did you speak in New York?
About 20 and something years ago. That time, there was Ilyas Farah in New York, and he invited me to give a talk.
Oh, so this was, okay, this was, I think, maybe even before I was at the grad center. Because I don't know.
I remember Ilyas Farah was at the College of Staten Island, actually, for a while. Yeah.
Okay,
all
that's
right. Okay.
Sorry, no, I had to ask. Sorry, but
okay.
So anyway, let me just start it technically. Significance of parameter in some schemes of axioms. So first, parameters, that are free variables in different axioms schemes in theories like Peano arithmetic, Zermelo-Frenkel, and others similar. If we have an axiom scheme, let asterisk means parameter-free part of it. I got acquainted with this topic just once coming across Kreisel, old paper, Survey of Proof Theory. And this is just a citation that says it's natural to study such things as the effect of parameter. So let's just, what is the effect? Just immediately, it's question, is the parameter-free subscheme really weaker, or it is in a way equivalent, right? I consider this question with respect to comprehension and choice in second-order arithmetic. First of all, just like a definition introduction, I denoted by DA second, it has different other notation. So natural numbers and sets of natural numbers. It includes Peano's axioms for numbers. Induction is in such complete form. Now, in this case, it is important because the induction as one sentence is not adequate in the absence of full comprehension. So induction like this, and the comprehension, CA, in parameters can happen, but CA star is a parameter-free subscheme. And accordingly, K piano, second piano arithmetic with star is a subsystem in which we have only parameter-free comprehension axiom. Now, just the same question. Is the parameter-free theory of second-order piano arithmetic strictly weaker? It happens that it depends on what do we mean by weaker and stronger. First, in the sense of consistency, the answer is no. That is, they are equivalent in the sense of consistency. This is Harvey Friedman old result. So he established that the theories are equiconsistent. The argument of Friedman is approximately like this. So let's start with a second star, and let's define constructible reals. Try to define them as long as we can. And with some help, with some other tricks, just the whole set of constructible reals, or part of it, it depends on some details, will be a model of piano arithmetic with parameters. So in this sense, the theory and the parameter-free subtheory, they are equiconsistent. Now, my approach is to compare them in the context of deductive strength. That is, just clearly, can we prove everything in the full second order piano from only the parameter-free piano? And in this case, the answer is that really the parameter-free subtheory is strictly weaker. So this is the result. And basically, piano arithmetic without parameters does not prove one very simple thing. Does not prove that every set has its complement. Model is actually very simple. So we start with the constructible universe, and we adjoin a Cohen generic sequence of reals. In this case, real is a subset of omega. Now, let's consider the set X, which contains all constructible reals and contains this set of reals, just only these reals, Cohen reals, countably many of them, without any attempt to close them until under any operation. So such a, well, strange, a little bit strange set, but it happens that X is an omega model of the parameter-free piano arithmetic. And of course, sets AN do not have their complement. To prove this comprehension without parameters, it's not that clear at the first glance, but it's based just on standard, more or less standard permutation technique. of the forcing, co-enforcing involved in this generic extension. But, well, this example shows that the parameter-free piano arithmetic is a little bit weak theory. That is, such a thing as non-existence of complements just makes this theory not that good. So let's try to do something else. That is, let's try to first adjoin to the parameter-free piano some good amount of comprehension with parameters. And this is much more complex theorem, much more complicated. That is, we take piano arithmetic without parameters, adjoin comprehension for schema 1, 2 formulas with parameters. This is just a small part of full comprehension, but on the other hand, it covers almost everything, whatever people usually consider within just in systems of second order piano arithmetic. If you look in Simpson book, then 90% of it is definitely within comprehension for sigma 1, 2 formulas. And the result is the same. It does not prove certain instance of comprehension with parameters. And now, how the proof is managed? There is, in the construction is divided in 2 steps. First step is what I call basic model, and then a certain sub-model. So what is basic model? I define it by means of some combination of product and iterated Sachs forcing. So how it works in this case? Index set, so it's finite tuples of countable ordinals. The empty tuple I exclude. The extensions will be cardinal preserving, so omega 1 is the same as omega 1A. And generic reals BS indexed by indices from this I. And they are defined in such a way that each next index, that is, we have some index S, finite tuple of ordinals. If we add one more ordinal, then we have a Sachs generic real over the previous real. Okay, B will sub empty tuple, simply empty set. Then the array of these reals are defined, and this is the basic model. So just in some general framework, so this is maybe called generalized iteration along the index set I. I call it arboreal iteration because this I is 3 in this case. 3, well, without just one element, without the empty tuple. Well, so let me just let me be more specific and actually define the forcing because it's interesting. Such forcing has such nice properties which allow just to circumvent the machinery of iterations, and it allows to define the actual iterated forcing in pure geometric way, so to speak. So let me show. Assume that Xi is a countable initial segment of this I. Then power set of omega is considered as Polish compact space, and so is power set of omega to Xi, just a product. Now, crucial key definition. Assume that H, which maps the space P of omega to Xi into itself, suppose it is homeomorphism. That is just simply continuous and 1-1 because this space is compact. We call it projection keeping. If taking any smaller initial segment and any 2 points in the space, if they coincide, if their projections to this smaller initial segment coincide, then the projections of their images onto the same initial segment coincide as well. So for every eta initial segment and for every x and y, we have this equivalence. Then we can consider just the range of H of this homeomorphism, just the image of the whole space under this map. So it's clearly closed set. And the forcing consists of all such sets. Well, it's quite clear that P of omega to Xi itself is set of this kind because we simply take H to be the identity. Now, dimension, it's not a topological one, but dimension in the sense of this definition shows the set is a subset of which exactly space considered. And now the order. X is stronger. Just what does it mean? It means that the weaker set, dimension of weaker set is smaller, but the projection of stronger set onto the weaker dimension is a subset of the weaker condition. Just you can understand this just in case when Xi contains just 2 points, that is, we consider something like a plane, planary set, and eta contains just only 1 element. So then sets of dimension 2, they are planary sets, and sets of dimension 1 are just linear ones. And the planary set is stronger as a condition if its projection down to the first axis is just a subset of the linear set of smaller dimensions. So this is very natural. So that's all. So forcing is defined and the order is defined. This is just inside L. And it works in the sense that it really produces general iteration of the Sachs forcing along this initial segment, along this index set I, such a splitting construction of Sachs, of consecutive Sachs real. So let me just repeat the previous slide. So we define index set. We define generic array of successively Sachs reals, in which sense that each real indexed by extended tuple is Sachs generic over real indexed by the previous tuple. And this is the basic model. Now,
Vladimir, could I ask a quick question? Is
Yeah.
it like, is there a way to characterize these X sub H sets, like these images of these projection keeping homomorphisms? I mean, I'm just having a hard time like grasping what they look like, or
well, if just once again, if this initial segment is psi, consists of 2 points, that is, we consider just planary sets.
oh, okay.
So actually, this definition is more or less equivalent to the following. We need that projection of it is a perfect set. First, we need that each vertical cross-section is perfect as well. Second, and third, we need that, the map which just sends a point down there into this cross-section, just a map from this power set of omega into the compact hull over it, right? This map has to be continuous as well.
Okay.
Because this first 2 things, that is perfectness of the projection and perfectness of the cross sections, is not sufficient to guarantee this continuousness of its structure. And in this case as well, projection keeping the homomorphism is just function from this plane to itself, one function, which just preserves just first coordinates. So
right.
You can say that it induces also one homomorphism of dimension 1.
Okay, yeah, thank you very much.
Right. This is okay. So this is basic model. Of course, in this model, everything is very nice, axiom of choice holds, and nothing we can just nothing interesting in matters of the axiom of choice. But now let's pick some part of the reals in this model, namely, successor lemma. What does it say? It says that, well, it says basically that the structure of success, it is defined in, it can be defined in terms of degrees of constructibility. More exactly, that each next B happens to be a strict successor in the sense that it is strictly bigger in the sense of constructibility order, means that Bs simply belongs, is constructible with respect to Bs extended by gamma. And also if any real is strictly L smaller than Bs gamma, then it is non-strictly smaller than Bs. So you can say that lower cone of the bigger one is equal to the lower cone of the smaller one plus its own degree of constructibility. So naturally, maybe it is called in some other name in the theory of partial orders. I call it strict successor. So each next B is a strict successor. And conversely, if any strict successor of some Bs in this model is of the form Bs extended by some ordinal gamma, modulo constructible equivalence. So it just will be a tool to define something in some model of the basic model. Now, let's define this set. So we have this array of successfully saxed reals indexed by tuples of ordinals. Set W, it consists first of all reals indexed by one-term sequences. So gamma is identified with the tuple with only one term, gamma, right? Then we add tuples of the form any gamma extended by any number of zeros. So this is, at this moment, it is still just a chain, because simply gamma is something like gamma extended by 0 zeros. But this is interesting. Index gamma, then some number of zeros, and then 1. In which case, any gamma, any n, but n has to belong to B gamma extended by 1. So we do not adjoin this B gamma extended by 1, but we somehow have it working in this set W. So this is W, right? It is, of course, set in this L of B. Now, we just close it in Gödel sense, close it down. That is, take any finite set of all these reals take all of them and intersect with power set of omega. So this is a subset of power set of omega. The claim is that this X proves this theorem. So we have to prove that X satisfies A star and comprehension for sigma 1, 2 with parameters, but also comprehension for some stronger relation with parameters. Let me now show just a graphical illustration, so to speak, graphical representation of this this construction. So first step, just we just consider this chain of just zeros, tuples containing 0 and then some more zeros. So this is a chain, right? And blue is the structure of success, or what is the same, the structure of that strict succession. Now, we have this real just around here, but we do not put it in the model. So let it be just 2, 4, 6, no matter what. Just to illustrate, I take 2, 4, 6. Now, we add splits at corresponding levels, 2, 4, 6, and further on. So in this case, look, suppose, consider just the Gödel closure of all of them. Now, this red real does not enter the model, but we can define it inside the model. Just to say that the set of all n's such that in the structure of strict succession, we have splits at level n. So obviously, this way we have the comprehension fails in such a extension. But on the other hand, you know, we have to prove that and comprehension fails with B0 as parameter. So we have to say that, well, let's take numbers n such that at the level n above B0 in the structure of direct succession, we just have splits. But unfortunately, in this case, we can define splits like this in a parameter-free way, because there is only one tower like this. So we just can say, just we eliminate this B0, we simply say that take the only tower that exists and consider numbers n, which such that at nth level we have splits. So this model is insufficient because the failure of parameter-free comprehension. So what we can do just to use this idea, but to get rid of this obstacle, we have to make the construction a little bit more obscure, just in a very simple way, by multiplying this construction omega 1 many times. That is, we adjoin B1, and suppose that B11 is some other set, and now we add a similar tower extending indices in index 1 by any number of zeros, and also add splits at according levels, just with respect to this, which actual numbers belong to this red, the corresponding red set. Actually, next tower like this, and so on, omega 1 times. And so this is just the graphical construction of the model I consider for this purpose. Just I repeat that earlier slide, how I define the set W, and how I define the set X. That is Gödel closure of this W simply, just with finite support, so to speak. Now, why X proves this theorem? So we need to prove parameter free piano, then comprehension for sigma 1, 2 with parameters, and we also need comprehension at some higher level with parameters to fail. So this is a kind of sketch of this. So it's a model of parameter-free theory, once again by the permutation technique. Model of sigma 1, 2 comprehension easily by Schoenfeld absoluteness. Then sets which were presented by red, that is indices gamma extended by 1, gamma being arbitrary ordinary countable ordinal. They do not belong to our set X by construction, but each of them can be defined inside X with corresponding the gamma, which is below, as only parameter. Just the same way as just explained. Just let me. So, for instance, I explained that this B01 is coded with parameter B0, just using splitting points, using the just investigation where the splitting points are and the corresponding numbers are just those which belong to this red set. So this is just how it works. So comprehension fails, and if we really want to know how far from it fails, it's a fourth level. So here it has to be bold-face because this parameter. So it fails at fourth level. Fortunately, so far there is a gap between second level where it holds, and fourth level where it fails. I don't know what happens at third level. Well, so this is just everything with theorem 2. And a problem. This is much more difficult thing. Prove that the parameter, the piano arithmetic with parameters, is not finitely axiomatizable over the parameter-free version. Well, more special form proves that if we assume comprehension with parameters at nth level, it does not imply comprehension without parameters at the next level. So this is, so far it's partially established by this theorem, because I cannot, as of yet, get a sigma 1,3 counterexample. Sorry, this has to be CA without asterisk. So this is without asterisk, of course. Well, so this is work in progress anyway. And just without going much into details, also about parameters in the choice scheme. So the usual form of axiom of choice in the second order piano, what is x sub k, dependent choice, and we can of course define parameter free subscheme, and this is interesting only with respect to countable choice, because for dependent choice it is known that the parameter free form is simply equivalent. Let me a few words about a couple of classical models. If we want to get a model of second piano in which the parameter-free choice fails, it's sufficient to extend L by Levi collapse below the first limit cardinal. And the counterexample will be pi 1, 2. There is also a bit more complex model for second piano in which the parameter-free axiom of choice holds, but the axiom of choice with parameter fails. It is also by the Levi collapse, but below Aleph omega 1. It's a more complex model, and I explained that what kind of parameters we need for the violation of AC omega. But anyway, the counterexample also turns out to be pi12 with parameter. But there is something like shortcoming of these models. We need to use cardinals out of the Peano arithmetic to get these two models. So this can be considered as a shortcoming as long as we want, for instance, to define such a model, this or this, by means only Peano arithmetic itself, without any appeal to any cardinal just begins with aleph 1. Say if we care about the consistency hypothesis, which lies behind the argument. And well, this basic model helps to solve this problem. So the different submodels of the basic model can be defined, which model just the negation of parameter-free choice. Then second model, parameter-free choice holds, but the negation of full choice. And finally, full choice holds, but dependent choice fails. Regarding the last model, there is a recent paper by Cy Friedman, Vika, and myself, where it is really solved, but by methods much more complicated. So there is some reason to get it by simpler methods. So let's just let me present this model for the negation of the parameter-free axiom of choice. So we start with the same L of B, the arboreal generic extension, the basic model. The index set contains all finite tuples of count of ordinals, but the empty tuple is not included. Now, let me define omega capital be the set of all initial segments which have finite height. So there is a number n such that the length of any tuple in this psi is smaller than n, just initial segments of finite height. Then I define W as a set of all restrictions of this generic array vector B to initial segments in this set. And then I consider sets hereditarily ordinal definable from this W, that is ordinal definable using parameters which are elements of this W, not W itself, but its elements and ordinal. So this class, it is a model of Zermelo differential without choice, of course. In this model, parameter-free axiom of choice fails. Why is this? It fails for a formula which says that, so we need to define a formula with two variables. One is natural number, the other one is real. So this formula says that the real has to be higher than nth level with respect to this relation of strict successor, strict L successor above the constructible level. And just because initial segments I consider are all of finite height, the right-hand side of the axiom of choice fails for this particular relation. And accordingly, the set of reals in this model is just a model of Peano plus the negation of choice, of parameter-free choice. And two more non-collapse models for just first to distinguish parameter-free choice and full choice, and to distinguish choice and dependent choice. They differ from each other only in that I take different sets of initial segments. So this one contains initial segments of finite height. And the next one, omega prime, is a bit larger, right? So it has initial segments. It contains initial segments which may be infinite in the total height, but each their part with the same leftmost ordinal is still of finite height. That is kind of, if you consider this as a forest, so to speak, then omega, previous one, needs that the forest is of finite height. And this one says that each tree must be of finite height, but forest itself can be unbounded. So, so this is omega prime. Then the second one, omega prime prime, consists of well-founded initial segments. So omega prime, every initial segment here is well-founded, of course, but does not contain all of them. And omega prime prime, we just consider all well-founded initial segments. Just two more non-collapse models. Accordingly, we define W prime, the restrictions of this generic array to initial segments in omega prime, and the same prime prime, right? And what is the result? the same method taken of hereditarily ordinal definable sets with parameters in this W prime gives us a model in which the parameter free choice holds, but the one with parameters fails. Why? Because we just can use the real with some index alpha as a parameter, and then get contradiction just similar to the first model. Well, and the other one is a model of Zermelo-Frenkel in which count of choice holds, but dependent choice fails. So this is actually Jensen's old technique when he proved that the same result for non-definable in the undefinable, non-definable case. And accordingly, reals in these models, they give us models of piano. The prime model gives a model of piano plus parameter free choice, but not the full choice. And the second one, choice, full choice, but not dependent choice. Well, so this is right. So, and well, conclusion. That is 5 models I was talking about. The first one is that one by means of the coenforting, in which not all sets have their complements, but still parameter-free comprehension holds. Second is one which I consider in more detail, that is parameter-free piano. Then sigma 1, 2 comprehension with parameters, but full comprehension with parameters fails. So these and following 3 items just by means of what I call this arboreal Sachs iterations. The counterexample here is sigma 1, 4. Then full piano and the negation of parameter-free choice. Here counterexample is 513, which is still not satisfactory because the minimal one should be pi 1, 2. And pi 1, 2 was obtained in a paper by Cy Friedman and Vika and myself in a recent paper. But these models are, of course, much simpler. Next model. This asterisk is wrong. That is full piano, choice parameter free for, but choice with parameters fails. And finally, oh, this is also a mistake. No star here, no star here, no star here. that is full piano, full choice, and no dependent choice. Counter exams at 513 in all cases here. So this is this paper which I cited a couple of times. Well, and there are consistency results that can be extracted in all 5 cases. That is, if second piano itself is consistent, then any combination, any of 5 combinations is consistent as well. So this is clean result without any appeal to any involvement of any cardinal, any uncountable cardinal. So this is, let me finish at this moment. Let me thank the organizers for Vika in particular for the opportunity to give this talk, and I thank everybody for interest and patience. Thank you very much.
Vladimir, thanks very much. Super interesting results. Before I ask other people if they have questions, I have a question. So can you go back to the previous slide for 1 second? Okay, so it seems that the construction for the second one can be done using Jensen's iterations of Jensen's forcing instead of iterations of Sachs forcing. Is it possible that you get a simpler counterexample that way?
Yes, I believe it can be done. Just, I mean, as a similarly defined submodel of the model of this paper.
Exactly, that's what I was saying.
So is the case for 3, 4, and 5. So this is my, like, I believe this is the case.
Yeah, because I was thinking about it, and it seems that because because you have a uniqueness there, instead of having to use the Sachsness property, you should be able to get a similar count.
Yeah, sure.
Yeah. Okay. Okay. Do other people have questions now? Okay, if not, then thanks again for this great talk. I mean, really interesting results.
Yeah, thank you. And let me add that probably within a week or maybe longer, I will send a preprint to archive, how you call it.
Oh yeah, archive. Yeah, I mean, I would be very interested to see the
it will be there. It's almost finished.
Yeah.
And thank you very much.
Yeah, and I'll think about the Jensen part of it. I think it should really lower. I think it should be the same, basically. The construction with just replacing.
Simply, in this case, the basic model is much more complicated.
I mean, is it really? It's just iterations, because Jensen forcing itself is more complicated than Sachs forcing, right?
Yes. And
I mean, only because of that, because otherwise I think the iteration is going to be exactly the same. I mean, it's the same. It's the three iterations with countable subtree. I mean, I don't see.
You know, it includes this whole machinery of iterated forcing, just, you know, and the Sachs iteration, it avoids it. and
Yeah.
makes everything geometrical and very clean.
Yeah, that is the main difference. I realized that there's a way to express Sachs iterations in this way that I don't want to think about because I like the other approach, but I prefer just thinking of it as iterations, as just Sachs tree iterations. But yeah, that is true. Okay, and you're our last speaker for the.
Can I actually, I realized I did have a question. Can I ask that before we
Of
quit?
course. Yeah, Cameron, go.
So Vladimir, so like, do you know whether any of these results work for like the set theory case? So if you want to do like, say like Kelly Morse with this full comprehension schema, whether or not you allow parameters? Because I know the Jensen forcing, I understand from Vika is hard to do it in inaccessible, but people do Sachs forcing in it inaccessible. So does it generalize?
I think so.
Yeah,
Right?
I am thinking about this, but so far I did not, have any progress, and I even
Okay.
probably did not try.
What fails? What are you trying? What are you? What fails? It seems like it should just go through. Other than the complexity part, the complexity part is an issue. I mean, you have to do something about that.
Okay, I don't know. I am cautious, very much cautious to say that it is just absolutely the same. So there should be some kind of small differences which would need to, some extra work.
So is the problem is the problem with the sigma 1-2 part? I mean, that's from.
I mean,
What about just this first result with the co-enforcing? That seems like it should be much easier.
Yeah.
That should just go through the same, right?
Will this work?
yeah, sure, yes.
Yeah.
Point, number one, yes.
Okay, but it's the later ones that are the issue, yeah.
When they work simply with Sachs forcing, there is one property of perfect trees, which says that, every level of it is finite. That is of cardinality less than countable, less than the height of it. If we just go to this uncountable but not inaccessible, then this sort of fails. Well, inaccessible.
Let me find there.
Yes, inaccessible height, this still holds. But
Yeah.
we also need to claim that the set of splitting nodes in this tree has to be closed in some sense. That is, if we have this chain which splits infinitely often, then it has to split in the limit point of this. Okay, so I mean, it's really interesting, and maybe I plan to sort of think about this, but so far I have no progress. So whoever have done much more, then probably I will just read anything of this if it is available.